Hello, folks. This is lab number 9 in week number 9. And on the agenda today, I have the following topics to discuss. The first thing that I want to remind you is a question that was asked by some students what is the kinematic inversion? They said that they had seen it in their machine dynamics book, or course, and they cannot understand what the kinematic inversion was, or they don't remember. Let me put it this way. When you have a mechanism, when you have a bunch of, let's think about it like that, when you have a bunch of links connected together through joints, which are also known as kinematic pairs, this makes a kinematic chain. For example, a bunch of links connected together with pins in the outer space, they make a kinematic chain, and they're kind of useless because if you apply a tiniest little force on it, this will begin to move. The whole thing will begin to move as a rigid body and may even rotate. Now, as soon as you fix one of the pieces, then you get a mechanism. Okay? So kinematic inversion means that how many different ways can we actually fix a link? Well, obviously, if you have 5 links, there's 5 different ways you can fix them. Fix link number 1, fix link number 2, number 3, number 4, and number 5. You get 5 different mechanisms. The question is, these are all called kinematic inversions, okay? Once you fix a link, it becomes a mechanism, and the kinematic inversion, how many of them you have, depends on how many links you've got. Now, are these all different? The answer is not necessarily. Let me give you an example of a 4-bar linkage that you're familiar with. Now, 4-bar linkage has 4 kinematic inversions because there's 4 different ways that you can fix things. Okay. Now, when you do that, you see that you either get double crank, for example, what you see in a locomotive where you have wheels turning and there are these crossbars which are turning with it. So you can have double crank, or you can have double rocker, or you can have a crank rocker, such as what you use in a wiper blade of a car. Now, in the particular case of 4-bar linkage, although there are 4 inversions, but there's only 3 distinct ones, because the distinct ones are double rocker, double crank, and a crank rocker. So that's what kinematic inversion is. Okay. Now, the second thing that we're going to discuss is Coriolis acceleration, and these other ones, and I'm going to worry about them later on. So let me go to the business of Coriolis acceleration that you saw in your dynamics class. Whenever you have a rotating object, and on it there is an ant, for example, that is moving, there will be Coriolis acceleration associated with this relative motion. So if you want to know what is the total acceleration of this ant, knowing that it is moving on that rotating object, the object itself is rotating and this guy is moving on it, then you have the 5-term acceleration formula. And here it is. For example, if you look at this body, which is, for example, we use it as a reference point, B is accelerating, for example, at B, and it's rotating, then the acceleration of the ant, think about this point A being the ant, is made of 5 terms. Acceleration of the body itself at this reference point B, and there is this guy which is called alpha crossed with R relative RA with respect to B. This is called Euler acceleration term. This is the centripetal because of the the motion, the rotary motion, and centrifugal. This is kind of the r omega squared that you're used to. There is the relative acceleration of the ant, the very last one, because the guy is walking on it or moving on it. Therefore, it has an acceleration relative to the point B, relative to this rotating system. And then there is this Coriolis acceleration, which is the cross product of the angular acceleration, angular velocity of the rotating body and the relative velocity of the ant. This is what is called the Coriolis acceleration. Okay. So what I want to do is a problem today which mimics this. So we have a cylinder here, which is mounted on this shaft, and this shaft itself is rotating about the space. So this is the ant that is walking on that piece, and the piece itself is rotating, in this case, very simple rotation, about this axis. Okay? Now, let me remind you, I mean, we already showed you what this thing is. It's 2 omega crossed with V relative, okay? But if you look at this particular situation, 2 omega crossed with V, this is V relative, this thing is a vector, of course, and if you take its vector, which will be in perpendicular direction to omega and v, and if you take its magnitude, is going to be 2 times the magnitude of omega times the magnitude of v. And for the particular problem that I'm going to be doing, I'm going to assume that this is turning at the 60 RPM, which means 1 hertz or 2 pi radians per second. So this omega in radians per second is 2 pi. And the ant is walking at the distance, at the velocity of 6 inches per second. So if you multiply this out, 2 times omega times v relative, you get the magnitude of the Coriolis acceleration, which comes out to be 75.4 for this particular problem. So you can think about it, although this is not, there is no force acting on that ant, but the ant, you can, if you're rotating with with the turntable or with this arm, you think that the ant will be feeling a a force of the acceleration to omega cross v times this mass. This is called a virtual force or the Coriolis force, which is not really there, but is perceived by an observer who's rotating with the arm. Okay? I strongly suggest that you go to internet and type Coriolis acceleration MIT OCW, and you see a bunch of beautiful videos there which actually shows it to you. We don't have the time to do that, and I hope that when the course was taught to you in the dynamics course 2 years ago, some of these things were brought to your attention, some of these video resources. But anyway, you can do it yourself now. Okay, so this is pretty much it. So I'm going to create these things. There is going to be a base, there is going to be an arm, and there's a color on it. Okay, so let's go ahead based on these dimensions. Although these dimensions don't have any significance, what is important is the angular velocity of this arm and the relative velocity of the ant compared or as measured by this arm. But anyway, I'll go with these dimensions. So let's go ahead and immediately save this thing. File, save management. This is save as. There is my desktop. There is my folder, and I will call this thing Coriolis. Coriolis. Let me start with the base. So insert a new part in there, and I'm going to call this thing the base. Properties, base, and base. Let's make it. All it is a cylinder. So on that plane, I will sketch a cylinder like that. And let me just dimension this so that I have a rough idea how big these things are. So this is radius, let's make it radius of 1. Okay, exit. Where's the exit? Right there. Pad it. I'll make it by point 0.4. Okay, so this is going to be our base. So let me change the rendering here so that we can see things better. This is the wireframe. Okay, so is that the one? Yeah, good. So we go here, insert, insert a new part in there, and I'm going to call this thing the arm. Properties, arm, and arm. This is the rotating arm that I'm talking about. Let's make it. On that plane, I will sketch a circle of radius 0.5 because I'm really consistent with this drawing here, although it means nothing. 0.5. Yeah. Exit. And I'm going to pad this thing by maybe 1. Okay, good. Now, I need to draw this arm that's sticking out of that piece that's sticking out of that. So I'll go here on that vertical plane. On this vertical plane, I will sketch a tiny circle here. Let me zoom in. Circle right there. Exit. Pad it. I think I made it 8 inches. So let's see now that this is totally irrelevant, this actual size of the thing. Okay, good, good. Okay, so now we're gonna yeah, so we're gonna go there all the way to the top, save everything. Let's do the color. So insert a new part, say no, and this is gonna be right click, properties, color. Color, I think it's like that, yeah. Let's make it. So what I'm going to do is I'm going to do it on this face. On this face, I will sketch. Let me fit this thing. I'm going to project that circle. There we are. Here's the normal view. Because it's going to be a cylinder, hollow cylinder, so I'm going to draw another circle here. Okay, exit. And we'll pad it by, I don't know, maybe 0.5. That may look a little bit shorter than what you see in the drawing, in the slide, but that's okay. Now, because later on I want to plot the Coriolis acceleration here, for example, what I'm going to do, I'm going to create a point there. While I'm in this color, I'm going to say create a point, and center of a circle is the method that I'm going to use. There it is. It's created there. So we go all the way to the top, save everything, and let's go assemble. Now, the first thing I'm going to do is I'm going to anchor the base. So there is the anchor the base, and then I'm going to move things apart so that I can see it. For example, I'm going to say coincidence between this axis and that axis. This is easy. I don't have to move it. And then coincidence between this plane and the bottom plane of the cylinder of the arm. Let me remind you, there's a trick that you can use in order to get to the bottom of that arm. If you put the cursor on the curved surface and use the arrows on your keyboard, which goes up, down, right, left, right, you're going to be marching through the different things that cannot be done. And I'm pretty sure this is what we want. That's what we want. Okay, this is going to become a later on. It's going to become a Revolut join. Now, there's nothing to update because I did not move things around. So I'm going to, now the only thing is that I'm going to translate this thing in the direction X so that it's easier to see what's going on here. Okay. I want this thing to be a prismatic joint because if I make it cylindrical, I know that this has to slide on this, but if I make it cylindrical, there is an extra degree of freedom that has to be specified. So if I make it prismatic, there's no need to do that. So here's what I'm going to do. I'm going to say a coincidence between the axis of this cylinder and the axis of that arm, and coincidence between the vertical plane, a vertical plane of the cylinder, vertical plane of the arm. Now, the reason, because I did things in a very organized way, I think, so I can do that from the tree. So the YZ plane, let me see now, the XZ plane, you can see that this is the XZ plane, not the base, not the base. Cancel that, not that. Let's try it again. The XZ plane of the arm, there we are, and the XZ plane of the collar, and this is going to make it a prismatic joint. Again, there's nothing to update because that's how these things work. Now, can we check this? In other words, can I go to the move toolbar, check this box, and then say, okay, let me rotate this. Now, of course, it's going to move, but the cylinder is not related to this movement right now. Later on, this is a 2 degree of freedom system. You can see that because the rotation of this arm and the translation of the cylinder are independent of, this is not a single degree of freedom, okay? A single degree of freedom system. Later on, we're going to tie them through the equations, okay, related to time. So that's fine. So let me cancel that. Fine. Good. Save everything. Now we're going to go to digital markup, DMU kinematics. Get the magic wand out. There's a magic wand right there. Oh, see, I forgot to say, let me try it again. I forgot to say create a mechanism. Try it again. New mechanism, mechanism number 1, auto create. You say, okay. Needless to say, you're going to have one Revolut join and one prismatic join. That's why the degree of freedom is 2. Okay, good. So now we're going to put the physics into the problem. Okay, so we go to f of x, click on the mechanism, and notice that there are no commands specified here. So this is time, no problem. That means I have to cancel this. I go there, Revolut, I make this thing angle driven. Okay. And I don't have to change this thing to 0, but I always like to do that. This is totally irrelevant. And this one, prismatic, angle driven, starting from 0, going all the way to 8 inches. Obviously, mechanism can be simulated, but there's going to be 2 sliding bars. So if you click on the simulation with commands, you see that there's 2 sliding bars. One of them is responsible for the motion, the angular motion. The other one is responsible for the motion of the cylinder. You can see that. Good. So now we're going to go to f of x and click on the mechanism. Notice that these commands show up. This is where you put the physics. So this is the angle. So I selected it. Add a formula equal to. Now remember, 60 RPM is 1 round per second. Yeah. Which means 360 degrees per second. But if you want, you can just type 1 turn per minute instead of writing 360 degrees per second times, Katia understands this, times the time Now you might say, well, the left side is angle in degrees, the right side is not in degrees, but it looks like CATIA will understand that. But if you have any doubts, you can always change that. Please try it yourself, see whether you like it or not. 360 DEG underscore S. If you feel more comfortable, there we are. Good. And this is the velocity, relative velocity of that cylinder. So add a formula and equal to, I think I said 6 inches per second, 6 in per s. This was given in the statement of the problem, per s per second, times time. Good. So now we have physics. Okay, so let's go and do a simulation with laws. Simulation with laws. Not here. Where is that? Right here. Simulation with laws, right there. We want to do it over a 1 second period, not 10 seconds. So we make this thing 1. And we say OK. And then we play it. It turns once, and this goes by 6 inches. You might say, OK, looks good, but how do I know the physics is in the problem? Well, we're going to have to create sensors. So we go here to, there we are, speed and acceleration sensor. You say, okay, reference product is the base. And the point is that point. Remember I created a point at the end of this cylinder right there? Say okay. Good. Incidentally, if you created the trace of this, it will go on a spiral, but I'm not going to do that. Okay. So now we're going to say simulation with laws, activate sensors. Okay, so let's see now. There is no such a thing as Coriolis acceleration. There is X, Y, Z component of the acceleration, and then there's the magnitude of the acceleration, for example, which doesn't say magnitude actually. It says, what is that? Linear acceleration. This is the magnitude. Okay, so let's actually do the magnitude. Now notice that I said yes, right? Notice that this is a constant rotation. Therefore, there is no Euler term. There is no alpha or there is no theta dot. Okay. There is a centripetal one because this is rotating, and there's the Coriolis one because the point is moving while this is rotating. So we're gonna figure this out. Okay. So let me move this thing out of the way, and we're gonna play this thing. Okay, and then we're going to graph it. All right. So what is the unit here? Let's make sure that inch per second squared. Very good. Okay. Per second squared. Good. So let's see if this whole thing makes sense. When this guy starts, it is already a certain distance away from the center of rotation. So definitely there is that term, the r omega squared. Okay, this is your r omega squared. You know what omega is? It's 2 pi. Okay, but there is an r because that point is already, I think, 1.5 inches or something like that away from the center of rotation. There's this term, but it's pointing toward the arm. It's pointing towards the arm. Okay, right. What do I mean by that? It is pointing, let me move this the other way. It is pointing this way. That is the centripetal one. The Coriolis one is going to be omega crossed with v, which means in the tangential direction, this way. Okay. So when you do the magnitude, both of these are combined and they're done as a square root of 1 squared plus the other 1 squared. So what I'm going to do instead, let me go back here. Let me rewind this thing. Let me go back. And here, clear the history, clear the history. For the selection, I'm not going to do the magnitude, because when you do magnitude, the centripetal one and the Coriolis one is underneath the radical square of each one of them. So let me say, for example, acceleration in the y direction. Linear acceleration in the y direction. Okay, there. Let me get rid of the other one. I think I already, let me get rid of the y. Y is good. The magnitude, I got rid of it. Oh, there, I don't want this. I just want the magnitude. I just want the acceleration in the y direction, which I selected right there. And then play it, and then graph it. Aha. Now, notice that what we have here is, uh, of course, this thing is, if you look at it, uh, let me see for a second, your 75 right there, 75 at this location. I know that I know that the Coriolis is in the y direction, and at this location, at the final location, I know that the Coriolis in the y direction, and guess what this value is? It is 70, whatever, 75 point something. Okay, so this location, if you look at it, halfway between these two, and it is going to be this calculation that I did for you. Please think about these things and work it out. It is possible to use different components, but it's going to take some time, and I'm not worried about it right now. Okay, so let's move on to our next problem. That takes care of, yeah. You see, there is this last item here. Instead of print screen, remember, suppose I ask you to generate this for me and submit it as part of your exam. You already know what to do. First of all, zoom out so that I can see everything, units and legends and things like that. Then you do a print screen, and then you create a Word file and paste it, and then you save that Word document with the name that you want, and just give me this one file, not this one plot, nothing else. And then you save it and submit as Word. But there is something else you can do. Look here. There is this, if you look at your windows, get your windows right there. See that right there? There is something called Tools, Image, Capture. Okay? Over here, it says Capture. Click. It creates a PDF file. Instead of you do a print screen and then paste it and then save it, what you do, you go to Tools, Image, Capture, and then save it. There's the full Coriolis, and I could call it my captured plot. So later on, when you submit your work in that folder, also upload that one PDF file. It's up to you. I don't care how you do it. I want a plot like this. Okay, whether you do print screen, paste, save, or whether you do Tools, Image, Capture, and then save it, it's up to you. All right. So let me close this. That's what this last item in the agenda is. Instead of print screen, one can use Tools, Capture, Save. Is it Tools, Image? I can't remember. Let's see. Tools, Image. Yeah. Tools, Image, Capture, and then Save. Okay? So, Tools, Image. Image. Capture. Okay, next item. We want to talk about the prelude to human builder. In CATIA, there is if you look at the start menu that you're familiar with, there is something called ergonomics design and analysis. And in here, there is a workbench called, or a module or app called Human Builder. And you can insert different mannequins. Uh, Here's a male, here's a female. They're different percentiles. In other words, you want a 50 percentile, normal one, or you want I don't know, 100 percentile, something that may be very skinny, etc., etc. And you can even have nationality. Believe it or not, it gives you the option of choosing Canadian, American, French, Chinese, and I think there was one other one I can't remember. It looks like that. They don't look very good, very basic. What they have done in the CATIA, in the version of the CATIA that is in the 3D experience, and I told you writing is on the wall. Everything you're going to be doing there, everything is the same except that the interface is different. Icons are different. But as long as you know your CATIA V5, then it's very easy to adjust it. They have arranged a bunch of new mannequins. And these new mannequins, as far as the wardrobe goes, as far as the makeup goes, you have an opportunity to adjust it. So you can use these or a whole bunch of other ones that you can use, different postures, etc. So I'm not going to do that. I told you that in this setup, all the joints in the bodies of the mannequin are made. Even the eyesight and things like that can be adjusted. And in fact, I've seen that happening with the capstone project. People who are doing Formula One or I don't know the other one, Mini Baja. They design the thing in CATIA and then they take a mannequin and put it there. And in fact, it is very useful because you can do a reach analysis. In other words, once you have an object here, you can ask CATIA to generate uh, the reach envelope, whether the hand can reach that point, etc., etc. Okay. Well, just to let you know that there is something like that. Now, the last item on the agenda for today is a wheel rolling on a path. And I'm going to show you one way of doing it. This is not necessarily the best way. There are other ways, but now I have already done something like that in the class. And in fact, your homework, in this week has to do with that. But here's the situation. I want to create a wheel that is rolling along a path that I've created. Now, the one that I did in class for you last week, I believe it was, this wheel was actually rolling along that side line, that edge. I want to show you what can you do to actually make it roll along a path. Okay, now, so let's go here. I don't need this. I don't need this. I'm gonna save that. So first, let me remind you of how to do it along that side edge. So we go here. Let's start with a product, because this is an assembly. Right? This is a mechanism. Insert the ground. Insert a new part in there. And I'm going to call this thing the ground. Properties. Ground. And ground. Okay, let's make it. Double click on a convenient plane. On that horizontal plane, I will sketch. Why don't I draw a rectangle like that? Exit, pad it. Okay, that's good. Now the wheel. So insert a new part. I'll call it the wheel. Okay, let's make it. So on a convenient plane, on that vertical plane, I will sketch. I'll sketch a circle. Let me give it a radius of 1. Okay. Okay, good. Now, exit, padded. That's fine. So let me make this thing 0.5. Okay, good. So now I want to make this thing roll on that edge. This is what I did for you last week. So first thing I want to do is make sure that these are flush. So let's go to the assembly design. I'm going to anchor the base first. The base is fixed, or the ground is anchored. So coincidence between this plane and that plane. And as soon as I update it, it moves this thing and makes it flush here. Now I want to bring this thing down, and there are different ways of doing it. One is to go, if you want, you can go to that sketch where you drew the wheel right there. You can go to the sketch and make this thing tangent to that line. That's one way of doing it. It's entirely up to you. Or I can go to my assembly and then use contact. Contact between this face and that face. And this internal external is important. One may look like what you want and one does not. We say okay and update, and obviously this is not what you want. Okay, so we go back here and you say don't do it internal, do it external. And of course, I'm pretty sure you know what it means, internal, external, externally tangent to each other. Okay, good. Now, what we want to do is we want to make this thing roll. So what we need to do is, first of all, remember I made this coincident with that. That's why I pushed it here and uh, made these surfaces flush. This will lead into a planar joint later on. That will give you a planar joint. This contact will not give you anything. Okay, so let's go to the digital markup, DMU kinematic. Get the magic wand out. Say new mechanism, auto create. Okay, and if you check, there will be only one planar joint right there. Now I have to do the roll curve joint myself. If I want this thing to roll, by the way, in order for me to see that this is actually rolling, you know what I'm going to do? I'm going to go back to the wheel. I'm going to go back to the wheel. Good. I'm going to draw a circle on that face, draw a circle so that I can actually see that it is rolling. Right there. Exit. How about maybe, I don't know, pocket it, pad it, whatever you want. There. Okay, good, good. So back to the mechanism. Now we're going to do a roll curve joint. Here's a roll curve joint. Look at all the joints that you've got. We have beat this thing to death, and pretty much all of them except for one or two we may have done. So we go to roll curve, roll curve. I want this circle to roll on that circle. And notice that there is a length-driven command here. This is why degree of freedom is 1. If I go to that roll curve and make it length-driven, not angle-driven, and we say OK, and you can see what's going to happen now. So if you go and try to do this manually, right there, okay? Now let me put it in 0 position. It really doesn't matter, I'll just leave it there, doesn't matter. Now, this is fine. I could have done this thing a different way. And what do I mean by that? Let me delete this join. Let me go and create a point. Let me go and create a point. But by the way, let me undo this. Let me undo that. What happens if I delete this? What if I deleted this planar join? Don't delete the children. Notice that the degree of freedom is 1. I need that planar join. Okay, so the way I'm going to do that is I'm not going to use the planar join. I'm going to draw a line up here, which is 1 inch away from the ground, and a point over there, and put that thing as a point curve join. So first of all, let's go to the wheel. Let's go to the wheel and create a point at the center of that circle. There we are. And then I go to the base or the ground, and I create a line which is 1 inch away from that. So let me do it like this. A line which is point and direction, point and direction. This is the easiest way for me to do it. You can do it any way you want. From this point in the direction X, right? Direction X. Okay, so let's make it like that. In this direction, and I want to go in the other direction. Come on. Okay, good. All right, good. So now we're going to go to mechanism, and we create a point curve joint. A point curve joint. The curve is this. The point is that. Length driven. If I say OK, this is still going to be, yeah. So it's going to be, I don't need to make it length driven because the roll curve was length driven. You can see what happens. Same thing. The choice is yours. I could have done it with a planar and roll curve. I can do it with a point and roll curve, etc. Now, this is going to help me to do the actual problem that I want to do. The actual problem was actually a path here, and you get the idea. Okay, so I draw this path. I can translate this path up here and make a point curve. So let's go ahead and do that. Now, first thing I'm going to do is I don't need this line, so I'm going to hide this. Okay, let me go to the assembly design. Oh, cancel. Let me go to the ground here. I'm in the ground. On that face, I will draw, for example, a path. And the path can be, for example, with the different ways of doing it. Let me do this. Let me do this. From here to here to here. Or I could have drawn a spline, etc. The only reason I drew a straight line here is easier for me to put that wheel in the right spot. So let me do this. Go to the assembly design. Oh, before I do that, yeah, okay. Let me go there. Let me go there to the assembly and put this thing in the right spot. So how am I going to do this? Assembly design. Good. So let me move these things. Let me make, for example, move these so that it's more reasonable as far as the location is concerned. In the Y goes like that. Okay. and then I'm going to translate it in the direction X, like so. Okay, and then let's see if I can make this coincident with that. So that line control this. Let's see if we can make it coincident. Well, or you can make a zero distance. Here's the offset. Uh, okay, sorry, between that and this, 0. So that it just, did it do it? No, that's not a good idea. This is not going to do. Let me do it a different way. Oh, okay, good. Let me try coincidence. Coincidence between this face and that. Let's see if it does it. Update. Okay, it did it. Now, I think I had another constraint here. Let's check one of these constraints. This guy, remember I made this edge coincident with that? Let me delete this. This is the one that's not working. And that message that I got was because it said that, hey, I can't do that. You're telling me that this to be on coincident pretty much with that, etc. But there we are. Okay, good. So now we're gonna go and I'll do exactly the same thing. First of all, I have to take this sketch and translate it up by 1 inch. So how do I do this? Well, first of all, we go to that part, okay? Because I want to take this curve, this sketch, and translate it up. Let's see if we can do it here. Maybe we can. I don't know. Translate. Let's see. That sketch. No, the problem is that I want to move that sketch, so this is not going to work here. So let's change workbenches. Let's go to generative shape design. Okay. All right. Let's do the translate here. Find the translate, and this you see in here I told you what to do. This is on the operations toolbar. Under the operations toolbar, there's the operations toolbar, and this is translate, I believe. Yeah, translate. You select that sketch and you say move it in the direction Z by 1 inch. 1 inch. This is why I make sure that this radius was 1 inch so that I can. There we are. You see this? There we go. Okay. So you're going to go back to mechanism, There we are. Let's get rid of these and do it again. So I'm going to delete this. I'm going to delete that. Okay. I'm going to make a point curve between this point and that curve. So where is this? Oh, I have to be in the digital markup, right? Yeah. Good. So let's do a point curve. There's the point curve between that sketch. The one thing I don't like is because these things, it seems that they're not connected. If necessary, we can actually go ahead and do a join here. Okay, we may have to do that. I'm not sure. Let's find out. Let's try it again. So a point curve between this sketch, right? This sketch, or this translate. The translate was, where was the translate that I created? That was under the ground, right? Let's see. Okay, no, I went to the tree. I went to the tree instead of selecting individual pieces here. I went to the tree on the ground, on under the ground part, select the translate, and for the point, I'm going to select that point, center, remember? And then I come here and do a roll curve. So we go here, do a roll curve between that sketch. Now that sketch was this, okay? And this edge. And then say, okay. Let's see how many degrees of freedom. Degree of freedom 1. I can either make this thing point, make this point curve length driven or make this roll curve length driven. I'll make the roll curve length driven, so in the other direction. The only thing is that I cannot flip the direction here. Cancel that, cancel that. Let's try to make this thing, this point curve one, length driven. Because this one I can flip. Won't let me do that. No problem. Okay. So we say okay. Okay, let's check it. The only problem is that this will go that way. I don't want it to go that way. Oh, no, it is okay. It is okay. Okay. So I did not have to worry about those. So this is how you can make it go along a